Okay, we're going to review L'Hopital's rule. So you've probably discussed limits before, and there was an algebraic approach to these limits, and you'd break them down algebraically through factoring or maybe rationalization, and then you'd evaluate the limit. Well, there is an easier way to do it, all right? And that is to apply L'Hopital's rule. And what that's going to entail here is applying the derivative. So here's an application of the derivative in using it to evaluate limits. So what we're going to do is we're going to look at the two functions f and g, just like this, and we're going to look at them in isolation, and then we're going to consider their derivative, so f prime and g prime. Now, why do we need to do this? Well, when you can't necessarily plug in a because it yields an indeterminate form, and typically what happens there is you have a 0 in the denominator, you will take the derivative successively until you can plug in or evaluate the limit. So once you've done that, you have your limit. If it's still not possible, then the limit does not exist. So let's go ahead and take a look at this very first example here, and I think you'll see how it works. Okay, so we're going to take the limit as x approaches -1 of x squared minus 1 over x plus 1. Now you should notice when you plug in -1 into the denominator, you get 0, which is not going to happen. This is an indeterminate form. Okay, so what we will do is we will take the derivative. So we will continue with the limit as x approaches -1, but in this case, the derivative of x squared minus 1 is 2x, and the derivative of x plus 1 is 1. Now we no longer have an indeterminate form. Okay, we can plug in the -1, we can evaluate the limit, in other words, and we get -2, our answer. Okay, so that's just briefly how L'Hopital's rule works. So let's go ahead and take a look at a couple more examples. All right, the next one is the limit as x approaches 3 of x squared minus 8x plus 15 over x minus 3. Again, plugging in the 3 in the denominator yields an indeterminate form. It's also 0 in the numerator, just for the record. So we're going to apply L'Hopital's rule, and I usually denote it like this to show that I've applied it. So let's write that little convention. All right, and then we get 2x again over 1, which again we can evaluate now to be 2 times 3, which is a positive 6 in this case. So then we take the limit as x approaches 3 of the derivative, which is 2x minus 8 divided by 1. So now we can evaluate the limit, and we get 2 times 3 minus 8, which is 6 minus 8, which is -2. And so there we have our answer. All right, let's continue. Just a few more examples. Next example, a trig problem. Let's see. We know that plugging in 0 in the denominator will yield an indeterminate form. So we take the limit as x approaches 0. The derivative of the cosine is the negative sign. So the negative sign of 7x times 7 by the chain rule divided by 2x. Yet again, another indeterminate form. So we will continue to apply L'Hopital's rule until we can get to a point where we can plug in it. You should see that in the very next limit that we get, we'll be able to plug in. So we're going to have negative sine of 7x. The derivative of that is going to be cosine. So it's going to stay cosine. I'm sorry, it's going to stay negative in this case. Times the original 7 that was there, times another 7 from the outside, divided by 2. So we end up with something that looks like, let's see here, -49. The limit as x approaches 0 of -49 cosine of 7x divided by 2. Now when we plug in 0, we get the cosine of 0, which is 1. So our final answer here is going to be negative 49 over 2. That is what the limit evaluates to. Okay? We're going to take a look at the next one, number 4. Cosine of x minus 1/2 over x minus pi over 3. Plugging in the pi over 3 yields an indeterminate form in the denominator. So we're going to get x approaches pi over 3 of negative the sine of x divided by 1. And so we plug in our pi over 3 into the sine. We evaluate negative sine of pi over 3 in this case, and we get a negative square root of 3 over 2. All right. And the last example here. Again, sine of 0 being 0. So what do we get? Well, we need to apply L'Hopital's rule, just like we've done in the last few problems. So let's see what that looks like. This one is pretty easy overall. We get the limit as x approaches 0 of 1 over the cosine of x. And now we can plug in the 0, cosine of 0 being 1. So our answer just 1 in this case. So some really nice examples here. Then applying L'Hopital's rule. Now I will tell you this. There are some applications of L'Hopital's rule in higher levels of calculus here. And you know, one thing that comes to mind is relative rates of growth. In other words, comparing how fast one function grows with respect to the other. We can use limits like this to help us determine which function grows faster or slower. All right, so that's in another video, but that's coming real soon. So as always, I hope this video was helpful, and remember, like and subscribe.